So thank you, first of all, everybody who's joined the call on time. Kudos to that. I'm Jesse Starita, and I'm kind of doing double duty, letting people come into this seminar and just quickly teeing up the talk this morning. So Christopher Neal, who is our director of research, is actually going to introduce the speaker, Jessica Garcia Nascimento. And I'll just maybe make a quick, maybe personal note that I've really enjoyed. We've had now for the past, I'd say, half dozen years, a number of Brazilian visiting scholars at the Water for Food Institute. I think it's maybe somewhat of a well-kept secret that we've had this many. Most of them have been at DWFI, but they've also been dispersed around different departments at UNL. But it's been a really great pleasure to work with them. They've brought a lot to the Institute. And then I think they've also been able to bring a lot to their host institutions by spreading the word that there's this, Water for Food Global Institute in Lincoln, Nebraska. And that has sort of created a pathway, if you will, between Brazil and Nebraska. So I won't go into too much details. I know Christopher.
No, I was going to say, and they find out that there's a couple of guys that speak Portuguese here, right?
That's right. That's right. We have a multilingual office, which is a definite bonus. So thanks again for joining us. I'll turn things over to our Director of Research, Dr. Neal, who can talk a little bit about the program and introduce Jessica.
Sure. Thank you, Jesse. Yes, as you mentioned, we've had quite a few students and scholars from Brazil. Up until recently, Brazil had a program that sent scholars abroad, right, so that they could work with researchers either on postdocs or on what we call the sandwich program, right? They're doing their PhD in Brazil. They come and spend 6 months to a year in the US working with a faculty member here, and then they go back and defend. And Jessica is in what is called the sandwich program. But we've had many students, and it's always been a pleasure to host them here, and they've been very productive. So today, Jessica, who joined us in February. She was barely a month here when the pandemic shutdown started. And so her whole experience in the first semester got affected with the shutdown. And we were able to extend her visa until the end of the year so she could at least have a little more contact, and things opened up a little, and it's been a better experience for her. And you'll see that her English is quite good. So anyway, she comes from us from the Luiz de Queiroz University of São Paulo Ag School. She is doing her PhD studies there in the Department of Biosystems Engineering, working with a faculty member there. Her undergraduate degree and master's degree were from the Federal University of Viçosa in Minas Gerais, which are also partners of ours, right? That university, we work on the project in the western state of Bahia with that university. And Dr. Everaldo Mantovani has been here as a visiting for a few weeks. So she got her her undergraduate in ag engineering at Federal University of Viçosa, and then her master's was at University of São Paulo. Is that correct, Jessica?
Actually, my master was at Exalc too.
Yeah, your master's was at Exalc, and in biosystems engineering, ag systems engineering, and now she's doing her PhD there. So the work she's doing is doing hydrologic studies in the state of Paraná, Brazil, and working with us on using remote sensing inputs to those hydrologic studies. And what she is presenting today is the gist of her PhD dissertation and some of the work that she's done while she's been here. So anyway, Jessica, welcome. I'll pass the floor to you so you can take over the screen with your slides. And I just, before you do that, I want to apologize to everyone and Jessica, that in about 30 to 40 minutes, I have to run off to my annual doctor's checkup. That was, you have to set these things up way before. So there was a little clash. And so Jesse will do the moderation at the end, okay? So Jessica.
I will share my screen first.
And I might mention, everyone turn off your mics, which you already have done, but just do that myself.
Okay. Hello, everyone. How Dr. Christopher New introduced me. I am Jessica. I am a PhD candidate at the University of São Paulo, ESALC. And the title of my project here is the Remote Sensing in Hydrology, a case study in Paraná, Brazil. So talking a little bit of me, I graduated in agricultural and environmental engineer in the Federal University in Viçosa, Minas Gerais, that is this state here in Brazil. And then in 2016, I moved to Piracicaba to do my master's degree and then my PhD. I know that you know a little bit of ESALC because, as Christopher said, a lot of our students usually come here every year, and also our professor, but it's beautiful university here in this picture. And first, I will give you a little bit a short introduction about the water resource management in Brazil, because it's the area of our study. But you can see that most of the things that I say here, you can apply also here in America and in other countries. Brazil has about 12% of the planet's freshwater availability. But in the North region, concentrate approximately 8% of the amount of the water available, but represent only 5% of Brazilian population. On the other hand, the regions close to the Atlantic Ocean have more than 45% of the population, especially the Southeast and the South here. And however, less than 3% of the country water source. So because of that, we have to make sure that we have the water resource management in a way that we can make sure that all the activities that we need, we have water available. For example, water available for irrigation, urban system, industries, and all the multiple uses. So in Brazil, as instruments commonly used in the water resource management, we use the charge for the use of the water and the water rights. But for that, we have to know about the water availability in our watersheds, in our rivers. So for that, we use reference stream flows. And as examples of the reference stream flows, we have the long-term average flow that is obtained by averaging the flow of historical series from a given location, and it corresponds to the maximum flow rate that can be regulated in a water course. And we also have the key 90 and the key 95, that they are related to flows and the percentage over the time, 90 and 90%, in which they are superset or equalized throughout the historical series. They are considered as minimal flows and they are obtained in permanence curves. So how you can see here, we need to know about the historical series. And to know that, we have to have measurements on the rivers. We have to have data to build our permanence curves and then obtain our reference stream flows. But here is a problem for us because especially in developing countries in South America, we have a problem about the density and frequency of observations because our systems are new, our management systems are new, And also these equipments are a little bit expensive, so we don't have too much of this in our area. So to solve this problem, we can optimize the information that we have in a watershed to predict the same information in a watershed that we don't know about the historical series using statistical approaches. In general, the flow predictions consist in to transfer the historical data between watersheds using models and regionalization techniques. And as an example of these hydrological models that we can use, we have the multilinear regression. That is the oldest method we use for that. We have machine learning techniques, for example, random forest. And we can also use the water balance equation to estimate the hydrological parameters. But for the first two, we can estimate the dependent variables that they are our references stream flows using independent variables. For example, the characteristics of the watersheds as slope and the area, precipitation and evapotranspiration. And the water balance we can use if we know about the other components of the equation, precipitation, evapotranspiration, and storage. And here, remote sensing help us because we can obtain all these characteristics and independent variables using its products. For example, the slope and the area of the watershed, we can obtain using the digital elevation model. And that is an image from our terrain. And the storage, you can use the data from the GRASS, that is a satellite that gives us the mass of the water in the world. And especially for the precipitation and the evapotranspiration, we can use the precipitation from iMerge. That's a new product. Its last version was made available to the public in October 2019. It has data from 2000 to today, and it has a high resolution, special resolution of 10 kilometers, and a temporal resolution you can obtain in 30 minutes daily and monthly products. So because of its high resolution, you can use its data in hydrological studies with great accuracy. And about the evapotranspiration, we have the Alexi data that is based on the two-source energy balance and allows the evapotranspiration estimative using remote sensing products. And two inputs derived from remote sensing instruments are key for this model, as the surface temperature and the vegetative cover fraction. And its spatial resolution is better than the iMerge product, is 370 meters. And its data is available in daily resolution in our Gloded platform in this address. So after this short introduction, our main objective was analyze the performance of hydrological models using remote sensing products for estimate the reference stream flow, K90, K95, and Km, and the annual discharge over the watershed in Paraná, Brazil. As a specific objective, that was the 3 chapters of my thesis, we have analyzed the performance of the daily and monthly iMerge products to estimate the precipitation in Paraná, used the iMerge mensal products and watershed descriptors in multilinear regression and machine learning models to predict the stream flows, the reference stream flows of watershed, and use the monthly iMerge and Alexi to estimate the annual discharge in the watershed using the water balance equation. So here I will present the Paraná state, Brazil, because it was the same area using the 3 chapters, the three studies. And the Paraná is this blue state here, and it is in the south part in Brazil. Its area, it's about 200,000 square kilometers. It has 399 counties and 11.5 million of inhabitants. The Tropic of Capricorn goes through the north of Paraná. So because of that, it's in the transition from tropical and subtropical climates. In the humid subtropical CFA, hot summer, and CFB, warm summer, according to the Köppen classification. Its main biomes are the Atlantic forest and the Cerrado. The precipitation in the state varies between 1,400 to 2,400 millimeters. The wet season is from October to March, and the most of Paraná relief is at an altitude above 600 meters. And looking for about now the economy of the state is the second largest Brazilian region that produce and sells grain, mainly soybeans, but also in the state is producing coffee, maize, and sugarcane. And the state is located in 3 hydrographic regions in Brazil: Southeast and South Atlantic in the coast, and the Paraná River basin in the entire continent region. And it's a very important hydrographical region in Brazil, because 44.6% of the electric energy production and transmission system is in this region. So our first objective was analyze the performance of daily and monthly immerse products to estimate the precipitation in Paraná, Brazil. For that, we used the observed data from the National Water Agency. We used 511 gauges, and the estimate data, we used the immerse version 6, and daily and monthly final run products that is available to the public after calibration. And our time series was from 2000 to 2018. To analyze the performance of the satellite product, we used the quantitative indices, correlation coefficient, determination coefficient, mean error, mean absolute error, and the root of mean square error. And we also analyzed using qualitative indices, for example, the probability of detection, that is the fraction of rain events detected correctly with the total number of events detected by satellite. Our best value is 1. We used the critical success index, that is the proportion of rain events correctly detected by the satellites to the total number of observed events. And our best value here is also 1. And the false alarm ratio, that is the fraction of occurrence of unreal events among the total number of events detected by satellite. And here our best value is 0. So looking at our first result about the temporal and spatial distribution of precipitation for the gauges, by the gauges and the immerse, we can see that it was very consistent in over all months in the year. In January and February, both detected more volume of the precipitation here in the coastal area. In October here in the southwest area, and in the dry season here in July and August, we both detected dry areas here in the north. And looking for the regression between the daily and monthly data, we can see that the monthly data was performed better than the daily data, with R squared equal to 0.73 and correlation coefficient equal to 0.85. And here is a very interesting result. Our qualitative indices was very, very close to the perfect. The probability of detection was 0.99. The critical success index was close to 1. And the false alarm ratio was close to 0. So it's a very good product. And the reason that one of the explanations for the best performance in monthly scale is because in the daily scales, we have more variability in the space of the precipitation. And also because of the immersed monthly product is recalibrated using gauges over the world. So it's available to the public after this calibration. And looking here, the spatial metrics evaluation of immersed products, we can see that in the entire continent, it was very homogeneous. But here in the coastal area, we had the worst, not worst, but the performance not so good as in the continent. We observed this in the qualitative indices and in the quantitative indices and qualitative indices too. And it can be explained because here in the coastal area, we have the mountains and the satellites have limitation to discriminate the adjacent pixels of land and water, resulting in signal contamination in mountain areas. But here we can see, looking the scale, that the qualitative indices was very close to the perfect in the whole Paraná. And as a conclusion of this first study, we have that the volume and spatial distribution of observed and estimated precipitation were consistent over the year for the monthly products of immersion. And the immersion has high correlation, accuracy, and low errors in statistical metrics at the monthly time scales for estimating the precipitation in Paraná. And because of that, we are going to use the monthly product in the next study. For that, our objective was use the merged product and watershed descriptors in multilinear regression in machine learning techniques to predict the reference stream flow in Paraná. We used 81 hydrological gauges from National Water Agency in Brazil, that is the agency responsible for our water resource management there. And we obtained daily data. So we average the daily data to obtain the monthly information. And that gives to us directly our long-term flow, that is the key here. And when you organize your monthly information in decreasing order and adjust it to a probabilistic distribution, for example, Weibull and log Pearson 3, you have your permanence curve and you can obtain your K90 and K95. And for that, we use a time series with at least 15 years of data and less than 10% of gaps. And we try to not consider the effect of the area in our stream flows. So because big watersheds tends to have more greater flows than the smaller one. So we divided all the reference flow, the KM, K90, and K95, by the area of the respective watershed, resulting in specific flows. And as I told you a little bit in the introduction, in these two methods, we have to know about the independent variables or characteristic, climatic and morphologic characteristics of the watershed. For that, we use as a climate descriptors, the mean annual precipitation from IMER6 and the landscape as drainage, the mean altitude, the mean Talweg length. Talweg is the longest river, the length of the longest river in a watershed. So we use the mean Talweg length, the mean slope, mean Talweg slope, the latitude and longitude of the centroids of the watersheds. And first, we applied our first method, that was the multiple linear regression in homogeneous hydrological regions. So we have to separate the Paraná in regions that has the same characteristics about that descriptors that I told you before, because this method is very good, but it's have to be applied in this kind of regions with similar characteristics. So for that, we used the K-means algorithm, and we separed the Paraná in 5 regions. In each one of these regions, we applied the multilinear regressions to estimate the Kn, K90, and K95. Here is an example of the in a general multilinear regression equation. So in each one of these clusters, we have three equations, each one to predict one of our dependent variable here. And second, we used the random forest, that is a machine learning technique based on decision trees, to estimate the reference stream flows. For that, we divided our data set with 81 watershed descriptors and dependent variable in train with 60 samples and in validation with 21 samples. And we evaluated the performance of this model. We'll evaluate the performance of the machine learning validation, the random forest validation, and the multilinear regression use the R squared, the link concordance correlation coefficient, the MAE, and RMSE, and the statistical bias, and the training. We evaluated using the R squared, the RMSE, and the MAE. And here, our first result for our multilinear regression, we can see here in this picture that our points, that our estimate data are very close to the line 1-to-1. That means that our model performed very well to predict our each one of these our stream flows that we wanted to know. And we can observe that looking to the R squared and the correlation coefficient, that was very close between the groups of the watersheds, varying between 0.74 to 0.75 R squared, and 0.84 and 0.85 to the correlation coefficient. And the errors were very close between the groups and were low, because we can explain this because of the magnitude of our stream flows here. So looking now for the random forest result, we can see that our performance was not was less was not so good as the machine learn or the linear regression, but it was good. And we observed that was easier to predict the long-term flow compared to the minimum flows. And also you can see that here for the minimum flows, our errors were very lower than to the medium flow. And an interesting thing of this method is that you can see which one of the descriptors is influenced, have more effect in the prediction. So for the prediction of the long-term flow, the precipitation and the watershed slope had more importance compared to the other descriptors. On the other hand, for the both minimum flow, the watershed slope and the longitude had more influence compared to the precipitation that was the first one to the medium flow. And we could explain this because the precipitation is the stream flow is an ultimate result of the precipitation, but in our minimum flow generally occurs in the dry season when the groundwater contribute to keep the flow in the rivers. So for the minimal flows, the precipitation is important, but the other two descriptors were more important. And as a conclusion, we had that besides that the fact that of multilinear regression overperformed the random forest in this study, the error metrics were very similar in both methods. Thus, the random forest could be applied as a tool for the reference flows prediction. And we are interested to know about the random forest because it can deal with the big data that we usually have in hydrology. And it's easy to apply because now we have a lot of packages available and they are free and you can easily implement in free softwares like RStudio and Python. And it will make our work easy because we don't have to spare first in hydrological homogeneous regions, and it will save us time. And lastly, our third chapter, our objective was evaluate the performance of estimated annual discharge of the watershed use precipitation and evapotranspiration data using the remote sensing products in a water balance equation. For that, we used 28 pluviometric gauges from the National Water Agency. The time series was from January 2013 to December 2014. And here our main limitation was obtain data after 2013 in Paraná using the website, ANA website. So that's why we are working with 2 years. We used the simple water balance equation, consider the inflow and outflow of water in a system. So the precipitation was equal to evapotranspiration plus the discharge and plus the difference in the storage. So as we are considering an annual scale, we consider this difference equal to 0 because it tends to be equalizing over the year. And so putting the key here and the precipitation here, we have that the key, our discharge was equal to precipitation minus the evapotranspiration. As the precipitation and evapotranspiration data, we use in remote sensing products. And the main advantage to use this method is the use of the free data from remote sensing in hydrological models as a tool for the water resource management. And as a precipitation data, we used the iMERGE version 6 in a monthly resolution that can be obtained here in this side. And as evapotranspiration data, we use the data from Alexi in the spatial resolution of 370 meters in a daily resolution. And we can obtain its data in our loaded platform in this address. So as our result here, we can see that the model, this simple model, worked very well to predict the discharge in the rivers in Paraná between the years 2013 and 2014, with R squared equal to 0.62 and the correlation almost 0.8, and with a little bit of percentage of to overestimate our flow, our discharge in the rivers, about like 12.9%. And we try to understand if the characteristics of the watershed could affect the performance of these models. So we separated our data set in 2 groups of area and 2 groups of slope. In small, when the watershed had area less than 5,000 square kilometers, and big when the area was bigger than 5,000 square kilometers, and about the slope in flat to soft wavy, the cliff slope less than 8%, and wave to strong wavy when the slope was greater than 8%. And comparing our statistical metrics here, we can see that the model performed the similar performance in these four groups. So then we try to understand if the cover, the land use could affect the performance of the model. And for that, we divided our data set in two groups based on the land use of forest, soybeans, and pasture. We separate in 25%, more or less than 25% to forest, and 15% to soybean and pasture. And we selected this number trying to make the two groups with similar numbers of the watersheds. So it was based on the median of the watersheds. And looking our statistical metrics here, we can see that for the forest, when we have more forest and more pasture, the model performance very, 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 very good, better than when we have less. And when you have less soybeans in the soil, you have a better performance of the model compared when you have more soybeans. And two explanations of this could be the effect of the filter effect of the forest and pasture. So these two crops, the forest and the pasture, have tended, they do a path in the soil, and that it makes the infiltration in the soil easier, and it reduces the runoff in the surface and try to make the stream flows in the river, the discharge in the river more constantly over the year. And when you have more soybeans in the soil, you have you have more change in the scenario of the soil during the year, and it could affect the estimative of the evapotranspiration, and also it can affect the storage in the soil that during over the year affecting the discharge in the river. So as a conclusion, we have that the water balance for the discharge estimation used only remote sensing products performed very well, with good correlation between estimated and observed data in fluviometric gauges, especially in watershed with forest and pasture in Paraná state, Brazil. Here are the reference, and thank you, everyone.
Thank you, Jessica. Thanks for sharing your work. And I know it's can be challenging to give a presentation in a first language, let alone a second language. So really well done in managing English and presenting all that work. I thought we have a really good kind of cross section of people from the Institute on the call, faculty fellows, and a representative or two from our Department of Natural Resources. So I wanted to turn things over to anybody who has a question. We're a small, intimate group, so just feel free to put it in the chat, or I can call on, I think Sagai has a question, and you can unmute yourself and go for it.
Okay, thank you. Thank you, Jesse, for your excellent presentation. I really enjoyed it. But I have a couple of questions. One is, from your analysis and results, precipitation is the highest one and the most important variable in your study. So why did you choose emerge for your study? And I can see that you have, the point is actually, why did you, there are other precipitation data sets estimated with the stations, for example, CHIRPS, which is higher resolution than the one which you used, emerge, which is 10 kilometer. My question is, why did you choose it? And also, that's 15 years. Emerge is 15 years. And the other, for example, as I mentioned, chips is 5 kilometers, and you have over 30 years of data sets. So have you considered that? That's my first question. And the good news is actually with the immerge, you have found high accuracy, which is really interesting. 0.85 correlation, which is really great. My question on that is, you compared the immerged data sets with gauges. How many gauge stations you used? And is it statistically significant? Those are a couple of questions. Thank you.
Hey, thank you so much for your question. Um, yeah, we chose the iMerge because it's a new project and we have a lot of studs with chirps and TRMM and other products. So we tried to use the iMerge because it was new. Its last version was available to us last year. So we thought that it would be great to have more studies using this project. And that's why I chose this one. And we worked with 511 gates to compare the iMerge, the daily and the monthly product.
How
Yes,
about the correlation? I said 0.85 correlation with the gauge. How many gauges did you use, and is it statistically significant? That was the second question.
yes, this one we used 511 state gates.
Okay, thank you.
There was a question in chat, Jessica. I can read it out loud from Doug Hallam. Did you consider splitting the land use by other means than relating to specific crops, such as by annual row crop agriculture versus perennial vegetation, such as pasture and forest?
Yeah, no, we didn't consider it because it was just our first study. Like we are just starting this study, and it is our first result. But now, yes, we have to consider this in our next step.
And Paulo, you have a question?
Yes, thank you, Jesse. Jessica, in your work, you are working with forest. When you are talking about forest, you are talking about natural forest or planted forest, or you put both together?
Both together. I put it both together.
Jessica, I have a question. You mentioned about the tools like Glodet and Alexi, some of which have been developed and promoted by the DWFI. But can you summarize or talk a little bit about how having access to these tools that DWFI developed, and then just the closeness that you had with the researchers here, how that has helped you advance your PhD research?
Yes, sure. The first thing was like that when I start to planning to come here and I was start to read about the work they were doing here. They didn't, I think they were just start the calibration in Brazil, like we are doing the calibration in Brazil of the Alexia now. And when I came here, we talked with Sami, and he was ready to help me to run this project in Paraná first. So it helped me a lot because he knew that I knew that I need that data, and he was very friendly and running it first for me. And you can obtain the data in our Glodet platform. You have to create your username and password, and then you will be accept, how can I say it? Will be allowed to use the data, and it's free.
Okay, Jesse, I want to make a comment for Jessica. Jessica, maybe in the future, for the future work, you can just divide in planted forest and natural forest, because the regime is totally different. In planted forest with pine and eucalyptus, you have trees growing a lot during a period of time in large areas. And in natural forests, you have a bigger diversity. And I think that could be a very interesting work in Paraná state. If you can make this division, I think that there will be a lot of people interested in this kind of data, mainly the people that is working in the pulp and paper industry. For them, this data could be very important. And so I think that this could be a very good step in the future for you.
Okay, thank you, Paulo.
Thank you, and congrats.
Thank you.
Thanks, Paulo. Anybody else would like to ask a question? So I'll make a closing comment, but Jessica, you might share with people your plans for the future. Will you be going back to Brazil, or will you stay here for a while longer to continue the research?
Yeah, my plan is to continue here for more time. I will defend my thesis from here in January 15th. If you are interested, I can share the link too. And yeah, that's it.
Great, thank you. And I'm gonna, in the spirit of sharing links, I'm gonna put in the chat box a link to our next seminar. It's actually, I don't know if it was just a coincidence, but both seminars have the same state in Brazil as their focal point, both Paraná. So you heard today about remote sensing, and then at the same time next week, Paulo Pires, who is our visiting research professor, who's on the call, of course, will talk more maybe about a legal perspective on water tenure and water rights in the state of Paraná. The link to register is in the chat box. If you haven't already done so, I encourage you to sign up and learn more about Paraná. And I guess with that, if I had a gavel, I would pound it down and bring the seminar to a close. But as I do so, I just wanted to thank everybody, and thank you, Jessica, for putting together such a comprehensive presentation of your research work.
Thank you, Jesse.